In this video, I want to give you one of the greatest triumphs of Newtonian gravity, and that is the prediction of the acceleration that we feel here on the surface of the Earth. So the question is, can we predict little g? So consider this situation where we have the Earth, and I have a small mass, maybe like a tennis ball or an apple or something, and it's just a little bit, of course this is not to scale, but a little bit above the surface of the Earth, so that its distance from the Earth's center is very approximately the radius of the Earth. All right, and we're just going to denote this object as little m. Okay, so now, first of all, what is the gravitational force felt between these two objects? Okay, well, that's just simply the law of gravity. F equals g times the mass of the Earth times our little mass, and because we're claiming that this distance between their centers, we're very close to the surface of the Earth. Okay, so if I just drop a ball from a meter off the ground, the radius of the Earth is roughly 6.37 times 10 to the 6th meters. Okay, 6 million meters. If I just drop it from another meter on top of that, it's negligible. Okay, it's absolutely negligible. It makes no difference whatsoever. So the radius of, or I'm sorry, the distance between our object and the radius of the Earth added together is just still very roughly, actually not very roughly at all, very precisely the radius of the Earth. And so we're just going to insert the radius of the Earth into this equation. And I want to know what the gravitational acceleration felt by the small object, the apple or the baseball or whatever it is. Okay, so how can I determine what that acceleration is? Well, remember that F equals ma. So ma is the force that this object feels. Pardon me. And since our masses of our small object are the same in both sides of this equation, I can cancel those out. And we know what the acceleration ought to be. The acceleration ought to be g. We've measured this in the lab. And so I replace a with g. Now, what this equation is telling me, this equation is telling me that the acceleration due to gravity is equal to the universal gravitational constant times the mass of the Earth divided by the radius of the Earth squared. So as long as I'm close enough to the surface so that the distance between the center of my object and the center of the Earth is still very well approximated by the radius of the Earth, then this equation will hold. And this actually holds up to a few kilometers above the Earth's surface. So g is equal to, little g, I should say, is equal to big G times me divided by the radius of the Earth squared. Now, the reason this is one of the greatest Newtonian, or triumphs of Newtonian gravity, is that once we were able to determine values for g, the mass of the Earth and the radius for the Earth, this equation should predict the value that we observe, and it does. Okay, so if we plug in the value of the gravitational constant, actually let me put it over here. If we plug in the value of the gravitational constant, I get 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. And the mass of the Earth is roughly 5.97 times 10 to the 24th kilograms. And we'll talk about how we measure that later. And then I divide that by the radius of the Earth, which is 6.38 times 10 to the 6th meters. And that quantity I need to square. And when I multiply all of these through, okay, I get 9.81, which is just what we measure in the lab with a simple accelerometer, okay, which is pretty amazing. And you can see that the units here work out because here I have kilograms, here I'm going to have kilograms squared, so these kilograms cancel out with one of those kilograms, my meters squared here are going to cancel out with the meters squared here, and I'm left with newtons over kilograms, and newtons over kilograms is just meters per second squared. So my units turn out. So measuring the acceleration due to gravity completely independently of gravity, or at least independently of the mass of the Earth and the radius of the Earth, just by looking at the acceleration of a falling object with either spark tape or a motion detector or something like that, gives you this value, or at least something close to it. Theoretically, hopefully it should be, this value should fall within your error bars, but you get something close to this value depending on your altitude and whatnot. But the point is that what we measure in the lab is what we can calculate with the known values of our constant and our mass and radius of the Earth. And so these two numbers agree, and that's the bottom line, and that is beautiful.